Hello. 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 We'll start our fifth day of ISLA 2022 in 5 minutes. We are waiting for more participants to arrive.
About when they can switch on their cameras. बैटरी ला के रखते हैं यहाँ पे exchange offer.
Okay. But he'll come after lunch. कल लेट Okay, so we are going to start our fifth day of ISLA 2022. We have Dr. Amit Kuber here. He will be talking about syntax and semantics, the second lecture of it. So, yeah.
Thank you, Anay. So, well, I'm going to start with a rant. Yesterday, when we asked everybody to switch on their cameras for a group photo, then you could do it. But when the speakers ask you to switch on your cameras, you don't. Why is that the case? We would like to see you. Yes. So, how do I pronounce your name? Shiguang?
Yes, Zhiguang.
Shiguang, right. So thanks. Thanks for switching on your camera immediately.
Sorry that I'm still eating.
Yeah, that's okay. Have a good breakfast or lunch, maybe
it's
lunch.
Lunchtime for me.
Lunchtime, yes.
I mean
lunchtime
China.
in China. Yes, okay. So, right. Whoever can show their face, yeah, if they have not just woken up, then I would be happy to interact. Yeah, really. Right. So yesterday we started talking about syntax semantics dualities, and we did a very basic, a baby example, that is propositional logic. Right. And today we want to understand more about predicate logic. And for that, let us quickly remind ourselves what kind of alphabet we are using. So alphabet, so this you have covered in Purvita's lecture, so I hope to get answers directly from you. Alphabets for first order logic. Sorry. I don't want to make it full screen. What is alphabet for first order logic? Please help me. Okay, so I'm going to partition it into two different things. Okay. I will write meta language and I will write language. So you have to tell me what lies in meta language and what lies in language. So language is something which varies according to different structures, and meta language, which is always there. It's at the higher level. Okay, so in the language, we have constant symbols, right? So constant symbols are, I'm going to write C. These are zero array relations. Yeah, I'm going to write the arity on top of them. Then function symbols, right? Actually, I can say that I don't need constant symbols. I can simply talk about function symbols, and zero array function symbols are precisely my constant symbols. Yeah, that's okay. So function symbol with arity n, and predicate symbols also I have got, which do not include equality. Yeah, so predicate symbols I'm going to write R, and they have some arity M, right? In the meta language, what do we have? Variables, very good. Then
logical connectives and the quantifiers.
Loudly, Devanjan.
And the logical connectives and the quantifiers.
Logical connectives and the quantifiers. Now I'm going to choose a very specific order of logical connectives and quantifiers. Yeah, so that let us do that properly. So I'm going to write T. So this T stands for top or tautology. Okay. Then I'm going to write conjunctions. These are finite conjunctions. Then I will write existential quantifier. After that, I will write the contradiction. Then I will write disjunction. After that, there is implication, negation, and finally, for all. There is a very specific reason why I'm writing them in this particular order. So, okay, let us first finish this and then I will come back to this. What apart from variables and logical connectives and quantifiers, what else is there? Parentheses are there. Okay, that's good enough. And the equality symbol, that is really important. Okay. Okay, so now the basic idea of categorical semantics is that the more structure you have in your category, the more structure, as in the sense of existence of limits and co-limits you have in a category, the more complicated formulas you can interpret in it. Okay, so that is our basic principle, very basic principle. So if my category has only finite limits, okay, so let me remind you what finite limits. So I think I'm going to do this in two different versions. Hopefully you will see the same. So these are classes of categories. And don't worry if I mean, I'm not going to give you the definitions of all of them. These are just some stronger and stronger categories. They have more and more structure and they will allow you to interpret more and more formulas. So first of all, I have got Cartesian categories. Okay, Cartesian categories are those which have all finite limits. Okay, I'm just going to write this. Finite limits. This is not a this is a proper definition, a category which has finite limits, which means finite products, binary products, plus terminal plus equalizers. If I have all this structure, then I will call my category Cartesian. Then I have a larger class of regular categories. This class of regular categories contains, in addition to these, very loosely speaking, it only contains one more thing, that is images of morphisms. So in sets, all of you are familiar with images. Yeah, given a set function between two sets, you take its image, and the image of morphism is basically the inclusion of the image in the codomain. That kind of structure you can have over here. Then inside, regular categories are still weak. You can't interpret everything. Then the next thing you have is coherent categories. In coherent categories, you have got a zero object, initial object, and you also have disjoint coproducts. Disjoint binary coproducts. Okay, I will be very specific. Disjoint binary coproducts, which means a coherent category contains everything that has been said so far. Finite means binary products, terminals, equalizers, images, initial object, disjoint binary coproducts. All of that structure is present there. The next one is pretoposes. Okay, I don't want to say a lot of these things, but these are like distributive lattices with an implication operation. Yeah, these are generalizations of that. So I'm not going to say more about it, but you can do a lot of things over there. And correspondingly, these are not just classes of categories, but in fact, I have got fragments of first order logic. Fragments of FOL, they are named exactly like this. So I have got Cartesian logic, regular logic, coherent logic, and here I have got full first order logic. But it is not classical, not necessarily classical. Okay, this is the kind of structure I have. Yeah, I'll come back to that. So Cartesian logic, now I want to go back to whatever we had earlier on the previous slide. Okay. So this over here we had written truth, then conjunction and existential quantifiers. So I'm going to write down some classes of like the fragments of logic accordingly. Essentially, the things which only use these two, they are called Horn formulas. The formulas which use only these two symbols and nothing else. So yeah, I mean, the classes of the fragments of first order logic depend on how many symbols, how many connectives and quantifiers you use. And that is the reason why I have written them separately. So Horn includes usually all the algebraic things. Yeah, you recall the definition of a group. it says that for all x, y, z, so you ignore that quantifier for all x, y, z. It says that x plus y plus z is x plus y plus z. So you are not really using anything, yeah, except for equality. Equality you already have and you are allowed to use. So which means we need very little logic, little strength of logic to actually talk about algebraic theories. You can think about rings in the same way. Yeah, all the things that some operation is commutative, some operation is associative, it has an identity, it has an inverse. They are simply equational theories. Yes. Now we are going to change that in a different way. That's the main feature of categorical semantics and how we write syntax also. Yeah, so you ignore that quantifier for the moment, and then we will do this. So this is Horn, and I'm mostly going to talk about Horn. Then I'm going to leave some space here, and I'm going to say these first three together, that is the regular logic. Then first five together, this is coherent logic. And this whole thing together, that is full first order logic. Okay, so there are some questions. So you can check. So approximately Horn should correspond to Cartesian, but Cartesian is a little bit more than that. You allow some existential quantifiers. So I'm going to write that only some existential quantifiers are allowed in that. Yeah, that is the Cartesian fragment. When I come to that, I will appropriately explain what that means. For now, I just want to show you the strengths. And for this reason, if you remember yesterday, I asked Professor Nick Bezanishvili in his talk, for Boolean algebras, you have classical propositional logic, right? For bounded distributive lattices, what is the corresponding logic? He said it's positive logic. What is positive logic? That you are not allowed to use negation. So you look at the same things it's the same flavor, yeah? You look at a fragment of propositional logic, that is your by removing certain symbols from your logic. Yeah, that is the positive fragment. So in the same way, we can, if our category has more and more structure, then we can interpret more and more connectives and quantifiers. So just keep this idea in mind. This is a covariant thing, that if you have more symbols, you need stronger, like more categorical properties, right? So now I should answer what is the meaning of not necessarily classical first order logic. So today you are going to look at Esakya duality, where it will be intuitionistic. So generally our full first order logic is intuitionistic, unless and until you put the restriction that the law of excluded middle holds. Yeah, this is the law of excluded middle. I'm just going to write it over here. Law of excluded middle says that for all x, yeah, it is this P or negation P, which means something, either something holds or its negation holds. Now that's why logicians are very careful when they talk. So I can say person X is good, or it is not the case that person X is good. Now this is the proper way of interpreting negation in semantics. Person X is good, or it is not the case that person X is good. If you go literally, yeah, to the negation of good, then yeah, I mean, we know we all live in a gray scale. Yeah, a person is good or a person is bad. Those are not the only two possibilities. We also have something in between. Yeah, a person could be good in some aspects, bad in some aspects. So law of excluded middle is not really preferred. in general, and therefore the categories in which we work, in those categories we do not assume this law at meta logic level, and therefore our logic is intuitionistic first order logic. That's the difference. This is the main difference between classical and intuitionistic. Any questions about it?
So in intuitionistic, we won't have two, is it? The two Boolean algebra thing.
Yes, you will have Iting algebras. Iting algebras instead of two.
Okay, so
I mean,
it'll be
still, So you can still talk about two-valued logic. But in general, so if you remember, Professor Mahua Banerjee gave you a general completeness theorem. She said that a formula is provable if and only if, the formula is tautology, like syntactic tautology, if and only if in each Boolean algebra, it evaluates to be 1. Each valuation gives you 1 in each Boolean algebra. So that is the Boolean algebra semantics. So similarly, in this case, you have intuitionistic, Iting algebra semantics.
okay.
Okay, so that is the major difference between, so the corresponding, so the category of sets is known as a Boolean category for obvious reasons. Because we have got power sets, and power sets are Boolean algebras. But in general, the generalized universes in which we interpret these full first order formulas, first order logic formulas, those are toposes. And the statement that the internal logic of toposes is intuitionistic, that describes it all. So you have to put one additional condition that law of excluded middle holds. Then you get from a topos to a Boolean topos where you have classical first order logic. So this is the major distinction between classical and intuitionistic. Any other questions about this? This is one of the important points. Yeah. Yes, we don't have this. That's all is the difference, really. And that means you have to change negation and the interpretation of negation and implication to something else. You will see more about that in next talk. Yes. I'm just writing it as a formula for now. That P, every formula is always less equal top. But in general, in classical, we assume that truth is less equal P or negation P for each P. But that is not true. Will be equal to top, which means top will be less equal this formula. The other one is anyway true. Okay, so I know I have written so much and I have raised more questions than telling you the answers, but this is the nature of categorical semantics. You have to understand that existence of certain limits and co-limits is an important part of the structure of category, and that gives you more strength to do more. Yes, Bhargav, you had a question.
Yeah, in regular class of category, what does it mean when we say it has all the images of morphisms?
I will explain something. I will explain one by one. There is a lot to be covered, but I wanted to give you a feel of what it is about before starting. Any particular questions? I will address them. Like questions about these classes, I will address them slowly as I go forward. But just something about the general idea. That's what I'm asking for right now. Okay, so now I'm going to leave this aside for a moment, and I'm going to connect it with orders, posets, and lattice theory. Yes. Dr. Sanjay Mishra, do you have any question? I don't think so. can you please move me? Yeah. Right. So all of us have seen partially ordered sets. So let me call that category as posets. And there is also a category of pre-orders. Yeah. All posets are pre-orders. You agree with that? So I have an inclusion functor from the category of posets to category of pre-orders. And on the way back, I can take the posetal reflection of a pre-order. So this is called a reflection functor. I'm not going to go into too many details, but the keyword will help you to Google it. That's why I'm giving you this. So given any pre-order, what is the difference between pre-orders and posets? Anybody? No antisymmetry, exactly. Which means if you think of a pre-order as a category, then there might be distinct isomorphic objects. Correct? Distinct isomorphic objects are possible. In a poset, that is not possible. So what you do when you go according to this reflection functor, you take this and you identify all the isomorphic objects and you make them into one. That's all you do. Yeah, you don't like multiple copies of isomorphic objects. So therefore you identify them, and that is a posetal reflection. In fact, this is an adjunction. I invite you to check that this pair of adjoint, like which one is left adjoint and which one is right adjoint. Yeah, the name reflection actually says it all. It always has a meaning, but try it out yourself. Okay, why this? Why fragments of first order logic? Why different classes of categories, and why partially ordered sets? Yeah, it doesn't make sense so far. But we are going to see that bigger picture today, how all these things are connected. Now, I am going to start talking about monomorphisms once again. So I gave you two exercises yesterday. I said that show that pullback of a monomorphism is monomorphism. If you have done that very well, if you haven't, then the tutorial session will have this problem. Yeah, we will address that once again. So monomorphisms are important. And I will say that I can define an ordering on monomorphisms. So given A1, A, so this is happening in any category, and A2, A, say that M1 is less equal M2 if, yeah, I'm going to draw a commutative diagram because that is what category theory is best at doing. This is M1, this is M2, and there exists a factorization. Yeah, there exists a map such that this diagram commutes. That is my less equal relationship. So what is important, the highlight is that the codomain is the same. I cannot compare two arbitrary monomorphisms. I can only compare monomorphisms with the same codomain. Okay, now this factorization, the dotted arrow is a monomorphism again that I invite you to check as an easy exercise. And you can verify very easily that in fact this particular order is a pre-order, this less equal. All monomorphisms, they form a pre-order with respect to this factorization relation. Okay, so every monomorphism is less equal itself. Yeah, I can choose A1 to A1 to be identity map. And whenever I have a factorization, I have this third one, which is again here M3, then I have this factorization, and then the composition, the entire composition will give me transitivity. composition of these dotted arrows will give me transitivity. So this less equal is a pre-order. Okay, so class of all monos at A with less equal is a pre-order. Now I'm going to take its Posetal reflection, and that is what I'm going to call sub of A. So if I'm talking about the category C, then this is the Posetal reflection of the above pre-order. Okay. So, which means what? Now let us examine one special case, that is the category of sets. Now you imagine 0, 1. I will use a different color for this example now. You imagine the set 0, 1. And I can take a morphism named star, from star to 0, 1, which maps star to 0. And I can take a morphism from delta, singleton delta, to 0, 1, which sends the unique element delta to 1. Now you have to tell me whether these two monomorphisms are comparable. I mean, look at this. Both of them have singleton images. So singleton should be identified, right? No? So Suyash and Vineet here are saying no. Any ideas from the online participants?
No.
No, okay. So these two cannot be identified. So what is the real idea? When I write sub, sub actually stands for sub-object. In the category of sets, the objects are sets, which means subsets. Right? So they correspond to subsets, which means these two are not comparable. These two maps are not comparable because their images are different. So now look at this idea, right? I can have multiple monomorphisms. I can change this symbol star to anything I like. Yeah, Vinod is here. The name Vinod can be put as singleton Vinod. And then we can map it to 0, 1, where that unique element maps to 0. Those two are going to be isomorphic objects in the pre-order. As long as two monomorphisms land with the same image, they are going to be isomorphic. So the idea of a sub-object is that it captures subsets. And that's all we need. It captures subsets. And now we have got hold of a poset. Right. So this is, this is a poset. In any arbitrary category, the sub-objects form a poset. In the in sets, it is the power set. Okay. So we have obtained something similar to a power set over here. That is the collection of sub-objects. Right. Now, we have put an exercise in the tutorial which says that if you have binary products, terminals, and equalizers, then you also have pullbacks. Okay. And now using that, I'm going to draw a diagram over here. So look here, look at this carefully. This is my A1. Suppose this is a, so when I'm particularly talk about a subobject, I don't talk about the equivalence class, yeah, or the isomorphism class of monomorphisms. I just choose one. Yeah, that's our usual practice. We identify equivalence classes with representatives. So this is nothing new, but I'm going to write this A1, A2. And if I happen to have pullbacks in my category, then I can construct the pullback over here, right? And we have seen the result that pullback of a mono is mono, which means this morphism will be a monomorphism, M2 dash. This morphism will be a monomorphism again, M1 dash. And this new object will again be a subobject of A. And this is what I'm going to call the intersection of A1 and A2. Is this clear? The intersection of A1 and A2, which means if my category happens to have pullbacks, then I have more structure on the subobject posets, that it is a meet semilattice. Because I have terminal object also, I mean, the identity morphism from A to A. So this is my meet of subobjects. And this is my this identity morphism 1A, which is a monomorphism. This is my top element in the subobject. So I'm going to go back to the previous screen and I'm going to write over here in a different color now that whenever I have finite limits, which means terminal byproducts and equalizers, then my sub lattice of subobjects of an object in that category will have a top element and I will have meets. Okay, now does that ring a bell? Yeah, you look at the Horn fragment of first order logic. We exactly had truth and meet. And now, just now I showed that if your category has finite limits, then you have truth and meet in each subobject poset. It is a meet semilattice with a top element. Let us go ahead. Yeah, I will come to regular categories a bit later. I'm still talking about these connectives. So yes, Bhargav.
Sir, can you go back to the previous slide?
Yeah.
In the sub, no, the one after this,
Okay.
the last line.
Okay.
Yeah. So in sub A, we have all the morphisms, right? Like it'll have some morphisms in it. So how is it that in sets that poset is the power set?
It won't have just some morphisms. It will have equivalence classes of those monomorphisms whose image is identical.
Are identical, right? But
Yes.
it'll still have morphisms in it. So how is it that it is the power set?
Yes, your question is valid. So in that case, when I'm identifying a monomorphism with its image, then I will call it the power set. So when I'm talking about this monomorphism over here from A1 to A, yes, technically speaking, my morphism is M1, and then the subobject is the class of M1. But what is the reality that I'm identifying in sets? I'm identifying M1 with the image of M1, which is a set, and therefore, which is a subset of A.
Okay.
That is the reason why we do that.
Basically, power set of A.
Yes, power set of A, exactly. Now, if my category happens to be coherent, then I said that we have disjoint binary coproducts. Which means what? What is the meaning of disjoint binary coproducts? So this is disjoint. I shouldn't use this color. I'm using blue. So disjoint binary coproducts and plus zero morphism, right? plus 0, sorry. I mean, 0 is the initial element, initial object. When I'm working in a coherent category, then I have these two. Now, because there is initial object, I can easily show with other properties that the unique morphism, the initial object is written 0. The unique morphism from 0 to A is a monomorphism. Therefore, this gives me the least element or the bottom element in sub CA. Yeah, the unique morphism from the initial object, because that is the definition of the initial object, that there is a unique morphism from that object to any other object. Right? So if I have that, then I will map it to the bottom element. I mean, that is the bottom element in the subobject poset, least element. What is the meaning of disjoint binary coproducts? That whenever I have A1 and A2, then I can write them inside the disjoint, I mean the sum. Then these co-projections are there. Yeah, the projections, all of you know, the dual version is co-projections. Then if I take the pullback, then the pullback as of them is 0. That is the meaning of being disjoint. Yeah, same idea as we know. Yeah. In sets, like two sets are disjoint if they do not intersect at all. So here we express that by saying that their pullback of their co-projections along each other is 0. Okay. So now I'm going to use some set theoretic intuition to construct unions of subobjects. Okay, so let us see what we can do. A1 and A2, I have got them, right? Then I also have A1 disjoint union A2. And I have these co-projection maps. Usually they are written as nu1 and nu2. That is the standard notation in category theory. Right? And this is my universal cone under this diagram. Yeah, you might remember from Deepankar's lecture that we need universal cones under the diagram. There is something in the chat. Okay. People can speak. Yes, Partha Pratim Ghosh. Are you stipulating the unique morphism from 0 to 1? Yes, if your category is a coherent category, then using all the properties, you can show that 0 to A is a monomorphism for each A. So in particular for 1 as well. I hope that answers your question. If you need some reference for this, yeah, I mean, just, I will just call it elephant. Yeah, so the book's title is Sketches of an Elephant, a Topos Theory Compendium, volumes 1 and 2. The answers to all these questions are in section A1. You use the pullback stability of regular epimorphisms. Yes, you know quite a lot. Yes. I'm trying to avoid saying many things. Thanks, Parth. Yes, I'm trying to avoid saying these things because I just want to give you the basic idea of more strength of categories than more strength of interpretation of fragments of first order logic. That's all. And then I'm connecting it with lattices. I'm not actually defining these classes of categories. Yeah, if I start doing that, I will be here for a week at least. So I don't want to do that. I'm just going fast. Okay, thank you. Right. On the other hand, now, suppose A1 and A2 are subobjects of A, which means there are monomorphisms like this. Let me call them M1 and M2. And then by the universal property of the coproduct, there exists a unique morphism here, which makes these diagrams commute. Okay. So what I have got so far, I have got A1, disjoint union A2, A, and this. And let me take you back a couple of slides. I said that while working with coherent, I already have assumed Cartesian and regular, which means I have images of morphisms. Okay, now think about this particular A1 disjoint union A2 as objects in sets. Then what will be its image factorization? What will be the object here? Huh? Something that contains both and something that is the least that contains both, which means it is the least upper bound of both of them, and that is how you define union. This is still a monomorphism. It is image factorization, so this is a monomorphism. So this is how I can define the image of this particular morphism. I can define the unions. So in coherent categories, I can get unions and zeros. Let me put that back over here, that I will get zeros and unions of subobjects. Now observe, when we went to coherent, the last two symbols that we dealt with are bottom and disjunction. Okay, if I have an Eyting algebra, I'm not going to say more about pre-toposis, yeah, because you haven't seen Eyting algebras. I was hoping that you would see them in yesterday's lecture of Nick, and then I can talk about them. But you have some sense of negation, some operation, unary operation of negation on subobjects in the subobject lattice. So far we have got a lattice, yeah, with disjoint, with meets and joins, and a bounded lattice as well, with top and bottom. Right. So therefore, here also, we have got, I mean, sorry, I shouldn't write 0 over here. I should write the bottom element. So we have got a bounded lattice so far. If the category happens to be a pre-topos, then that will allow you to have an implication and also negation of subobjects. So therefore, you will complete it here. I'm not going to say more. Okay. Because that will just raise more questions. So now what remains? If you compare it with this, what is remaining? There exist and for all, right? For there exist, I'm going to use these images of morphisms. So tell me if you have any questions about this overview. Okay. So in a coherent category, so far what we have shown, that we can do unions. It's a bounded lattice, right? If there are no questions, let me proceed. And the title of the next topic is something that I gave for student presentation: quantifiers as adjoints. So how will I interpret quantifiers as adjoints, right? So this is also interesting. And for now, we are only going to work in sets to build your intuition, and then we'll come back to all categories. So suppose I'm working with a morphism. I'm given a morphism in the category of sets F from A to B. Then actually this induces a morphism from sub B to sub A. All the subsets of B will naturally produce a subset of A. Under what operation? F inverse, correct. I'm going to call that F star. In an arbitrary category, what you can do, if you had a B dash, a monomorphism over here, then you take a pullback of that. Yeah, in a regular category, you have all pullbacks, so you can take pullbacks, and this will give you this functor. So this will be A dash, and this will be a pullback diagram, and this will be a subobject. This is exactly what happens in the category of sets. Pullbacks allow you to pull back the subobjects to another subobjects. All right. Now, the existential quantifier corresponding to this morphism is actually a left adjoint to this. So I'm going to write that. Yes, somebody is saying something. No? Okay, so I'm going to call this morphism, there exists some F. And that is a left adjoint to this. Okay, let me write down what I'm really doing here. This is all confusing in the first go. So given any subobject of A, let me name it A prime, then this is less equal B prime if and only if A prime is less equal F star of B prime. I have simply written down the definition of a monotone Galois connection, which is, I mean, these are both posets. So between posets and adjunction is nothing but a monotone Galois connection. I have written down the definition. So always remember, the left adjoint usually crosses the comma in the home set, and it becomes the right adjoint. Yeah, there exists F appears on the left, F star appears on the right. Right. So what is really happening here? If you put, we have to experiment a bit. I'm always bad. Do you remember which one we have to substitute? A prime equal to A. Yeah. If I substitute, yeah, put A prime equal to A, what will I get? There exists sub F of A is less equal B prime if and only if A is less equal F star of B prime. Okay, so look at this F star of B prime. What's A is less equal to something in the subobject poset, which means that it has to be equal. So A is equal to F star of B prime. We have to take, yeah, I mean, on this side, the condition is that this particular object is less equal all such B prime, which means intersection of all of them is precisely this. Which, can you convince yourself, this is precisely the image of F. Okay, so this is image of F. And in regular categories, we have images. Let me write down in general what this does. So there exists sub F of A prime is the collection of all those B primes, of all those B's, such that F inverse of B intersects A prime. Which means, in other words, where is this existential quantifier coming in? It says that there exists a point in the fiber of B which lies in A prime. Okay, read this statement as there exists a point in the fiber of B which lies in A prime. And more category theoretically, how will I describe this? I mean, normally I would just take A prime, then I will take A, the monomorphism. Then I will take F and I will take the image of this composition. So image of Fm is this is my there exists F of A prime. You can check these two are the same. This definition only works in sets. Yeah, not otherwise, but in general, this is what you do. You construct images of these compositions. And when my category is very rich, like it's a pre-topos, then in that situation, I have this for all F as a right adjoint of the pullback functor F star. And in sets, once again, I will give you the description that all those B's in B such that F inverse of B is totally contained inside A prime. So once again, try to imagine what is happening here. It says that F inverse of B means for all points in the pre-image of in the fiber of B, they are in A prime for all. Yeah. Earlier it was there exist, here it is for all. So this is how you interpret these two quantifiers. So this is in addition a property of the category. I cannot just look inside a subobject poset and say that there exists is here. Yeah, I have to look outside, like I have to connect it with the morphisms in the category and then using this. So quantifiers are really adjoints. And now we have finished looking at all these things. So here I just have a meet semilattice. Here I have a bounded lattice. Here I get Eyting algebras. And in between, because we are interpreting these quantifiers, we have more structure. So there is no structure on sub of A, but I'm just putting more restrictions so that I can interpret quantifiers. Is this like more or less like the vague idea clear? Any online participants, like, do you have any questions? Yes.
So I have a question.
Huh?
So I have a question. So in the interpretation of the meet and the join, there seem to be some asymmetry in it.
Mm-hmm.
So for the meet, it's interpreted as a pullback, while the join is interpreted as a co-product. So it seems that they are not symmetric.
They are not symmetric. Yes, that's true. They are not really symmetric. You like having finite limits is a weaker thing. But in addition to having finite limits and images and binary disjoint coproducts, like that's a much stronger thing. If you want symmetry, I can tell you something about that. Yeah, this diagram is both. So A1 intersection A2, A1, A2, and A1 union A2. This diagram with all monomorphisms, this is both. If your category is coherent, then this is both a pullback as well as a push out. Maybe this will help you to see that there is some kind of connection, like symmetry. This is both pullback and push out. Is that okay, or you have some other question?
Yeah, that's my question. Thank you.
Okay. Anybody else? Yes. Yes, Parth, please say.
Yes, since you have already put regular categories in between, but there can be structures where you have, see, you are putting in distributivity also. If you go to your previous slide,
yeah,
you are putting in distributivity very inherently
Yeah.
But there can be cases where the subobject lattice is not distributive at all.
Yes, that is true.
And when you come to pre-toposis, not only this, so it manifests as extensivity.
Yeah.
So there can be worlds which are beyond extensive. For instance, most geometric cases are not extensive, are extensive, but algebraic cases are not extensive.
Yeah.
So that's the real observation, that this picture actually is much more representative of the algebraic side rather than the geometric side of the study.
If by geometric you are referring to infinitary logic, I am purposely not mentioning anything about it over here.
Not only infinitary logic, but actually the places where regular epimorphisms are not pullback stable.
But then
So-
you cannot, I mean, you cannot call them regular categories anyway.
Yes, exactly. So it's beyond regular categories.
Yes.
Correct.
I mean,
Correct.
at that time, you'll just treat them as Cartesian categories and not worry about interpretation of existential quantifiers.
Existential quantifiers can still come through factorization systems.
Yes. And in Cartesian categories, you have some existential quantifiers. But in the definition of a regular category, you probably know that we need this. I think you already said that we need pullback stability of images.
Yes. Correct.
Yeah.
Right.
Yeah, that's true.
Yeah, correct. Thanks. Yes.
Okay. May I know where you are from?
I'm from South Africa.
Okay, thanks. Right. So any other questions or comments? I haven't yet connected with logic properly. Yeah, I have just dealt with syntax so far. That I told you that these are the classes of categories in which you can interpret these fragments of logic, but I haven't said how. Now I have to do that. I took much longer than anticipated for this whole. Huh? Parentheses are used in construction of formulas and terms, but not here. Parentheses do not have any interpretation. That's for our understanding to club things together. Right. So now I will go back here. I will give you a very brief idea of what's going to happen. A predicate symbol is going to be interpreted. So I will have a structure. Okay. What is the interpretation of this? Of all these symbols. Yeah. Roughly, I'm going to write down interpretation as Purvita explained. Yeah. In sets, you have a domain of discourse. So I will have an object in a category, in an appropriate category. Yeah. Depending on what you wish to interpret. In an appropriate category. So belong to C. I at least assume that it has finite limits. Yeah, that is my basic requirement, because immediately you will see why. A predicate symbol R will be interpreted in M as a monomorphism to M to the M. A monomorphism to M to the M, which means I should be able to construct products, M-fold products of the object M. For that, I need finite limits. Okay. A function symbol will be interpreted as a morphism from M to the N to M. This morphism is the interpretation of my function symbol. In particular, a constant symbol will be interpreted as a morphism from M to the 0 to M. M to the 0, what is it? Terminal object. Yeah. So in particular, a constant symbol will be a morphism from 1 to 0, and that is the interpretation in M. Variables. Now, variables play a very important role. I'm supposed to, I'm supposed to explain something else, but Look here. This is one symbol that we haven't interpreted so far, but the name should ring a bell. What is the corresponding category theoretic construction?
Equalizer.
Exactly. So these will be interpreted as equalizers. Of course, parentheses don't play any role. Yeah, then that's just for our help. Variables will be interpreted as projections. But for that, I have to make some concept clear. No, belonging to is not there. The purpose of categorical logic is to get rid of set theory. There are no elements. So that is the important idea that, oh, that means it's an object of C. Belongs to C means an object of C. It's an object of C together with this structure. Okay. So equality stands for equalizers. Now variables, on the other hand, they stand for projection maps. Now, I will again make this slide more dirty, but I will simply write down, suppose my language has binary function symbol and I want to write down commutativity. Then the corresponding syntax is for all xy, x times y is equal to y times x, right? But if I start using, even for simple algebraic theories like this, if I start using this for all symbol, then I always have to interpret in pretoposes. This is too much of a restriction. In first order logic, we don't care. Like the classical model theoretic interpretation, set-based interpretation, we don't have any problem with this. But categories do not necessarily have this much structure. And therefore, we adopt a more succinct sequent notation. So whenever I want to say that this happens, then I'm going to write that truth entails over the context xy that x times y is equal to y times x. This is my new way of writing the same formula. So what is the idea? That I set up a context for writing all my formulas. And in that context, I do not put a universal quantifier. Yeah, I simply deal with those objects themselves, and then I do this. Right? So that gets rid of the strength of the formulas. And then I can interpret it simply. It's very simple to write down xy is equal to yx. Now I'm going to do that for you on a new slide. Okay.
So, but won't the context become a quantifier in that case?
No, context is not a quantifier for, so that's why I'm going to start writing down my formulas and terms in context. So now terms in context, interpretation of terms in context. Sorry, I've messed up the whole spelling. So context is some finite sequence of variables which is suitable for all for that formula. Those variables need not appear in that formula or term, but all variables which appear there are already contained inside the text. All the free variables in that formula are contained inside the context. Okay. So that what are terms? Do you remember? What are terms? Loudly. Right. First of all, a variable is a term. Yeah, a variable is a term. So I'm going to write that a variable is a term in context X. Yeah. So this is my term. I'm always going to write the sequence of this is my context and this is my term. How will I interpret it? If I'm working in the context x1, x2, xn, then it will generalize function symbol. So x dot x, the interpretation of that in M, maybe x bar I will write. Yeah, sorry for that. I should write a context which is suitable. If my context is x bar and xi is one of the variables in that, then I will write its interpretation in x bar as a morphism from M to the length of x bar to M. This is xi, and this is my ith projection map. So I'm only going to pick that particular element. If I'm working with XYZ and I want to know what Z is, I will take the third projection and that will give me the value of Z. That's precisely what is happening here. If my term happens to be more complicated, yeah, that it's X bar and then it is F applied on some terms which already exist there. So T1 X bar and then Tm X bar, where let's say this is an M array function symbol. Then what should be my function? My interpretation of this term. So interpretation of this term X bar in context M, it again has to be a morphism from M to the length of X bar to M. Right? It's again exactly the same. How do we do that? Finally, at the end, we are going to use composition in categories. Yes. Arity of function, yes. So arity is M. I am taking M arguments. M arguments. So that is, yeah, that is correct. So I'm going to put M to the M in between. Okay. M to the M is there. And this is the interpretation of the function symbol. And earlier, what do I need? I need a map from M to the length of X bar to M to the power M, which means by universal property of products, I need M maps from M to the length of X bar to M. And those are the interpretations of already existing terms, which we have defined inductively. So this particular tuple is X bar dot T1 interpretation and dot dot dot. This is X bar dot Tm and its interpretation. So this tuple of morphisms is what I'm going to use. I know this is really very confusing, whatever I'm writing. It looks very complicated, but let us do an example. Okay. I think you will be happy to see an example. So let us consider that our language is that of groups. And I'm going to take only one binary function symbol. And now I want to interpret y dot x in the context x dot y, in the context x comma y. Okay. So what is my term? Term is in the context xy, it is y dot x. I mean y plus x. Yeah, yeah, that's okay. What is its interpretation? I will simply take M power 2. Think of it as the universe or the domain of the group. M to the power 2. Then I have to land inside M. So the arity of this function symbol is 2. And the length of this is 2. So this 2 is what this 2 is. And this 2 is what I'm going to write in between. Then from here to here, I simply have the interpretation of the plus. And earlier, what I have from M squared to square, the map is x comma y going to y comma x, because I need to add y and x. X comma y going to y comma x. So this is the pair. Yeah, I will write that down. It is the interpretation of x comma y, y, and x comma y, x. I mean, this pair is required. But what is the interpretation of x comma y? Y. It is the second projection from the first line. So this map is pi2 comma pi1. So this is the so-called twist map. Now yes, Purvita?
Actually, we just wanted to tell you that why you are not putting a over a, that you actually talked when you were talking about the function symbol.
Right. Okay, I can put m over here, but I don't want to write it in interpretation because my interpretation symbol already includes a superscript. Yeah. Okay, so this is pi2 comma pi1. Yeah, so is this okay? Then you take pi2 comma pi1 and then compose with this interpretation of the plus symbol, then you get y plus x. I hope this is fine. Yeah. And in sets, you can verify this is precisely x comma y mapping to y plus x. Right. So this is the interpretation of terms and interpretation of formulas. I'm quickly going to say that. So suppose my formula phi, interpretation of formulas in context. So remember what I said yesterday. I said that terms generalize function symbols because their interpretations are morphisms, whereas formulas generalize predicate symbols or relation symbols because their interpretations are sub-objects. Right. So interpretation of formulas in context. Suppose my formula is x bar T1 x bar equal to T2 x bar. This is a simple enough formula. Then I have, so m to the power length of x bar, that is always my codomain. Maybe I should go back a bit and remind you that the interpretation of this r to the power m is a sub-object of m to the power m. Yeah, so interpretation of relation symbols we already chose to be sub-objects. And now we are worried about formulas in context. So let us see what happens. So this is m to the power length of x bar and m, and I have got two morphisms. From above, I have got two morphisms that I have a interpretation of x bar, T1 x bar in M. And I have interpretation of x bar, T2 x bar in M. And then I have got two parallel morphisms. And we decided that the interpretation of equality will be equalizer. So if I take the equalizer of this, then in x bar T1 equal to T2, the interpretation of this is going to be the equalizer of these two morphisms. Maybe too much to take in on the fifth day if you have never seen category theory before. But this is why, I mean, to tell you what categorical semantics is, this is why the first category theory lectures, 3 category theory lectures were designed in that way, bombarding a lot of information so that at least on the last day or second last day, you can appreciate this, that this is the equalizer. Okay, so normally now what we do for the axiom for commutativity, we say that x plus y is equal to y plus x, right? So x plus y, y plus x, we have already seen what that morphism is. X plus y is simply interpretation of. So instead of pi2, pi1, I will have pi1, pi2, and then the interpretation of plus. Pi1, pi2 is nothing but identity. So it is basically simply the interpretation of plus. And then we are going to take its equalizer. Okay. Now, before I go to relation symbols, like arbitrary relation symbols, I want to show you something.
So you have 10 more minutes.
Yes. Yeah. Oh, thanks. 10 more minutes. I don't think I'll finish this today. This is a lot of content. Right. So let me remind you that how we are going to write down the axiom of commutativity. We are going to say that x plus y is equal to y plus x. In general, whenever I write the sequent that phi1 entails over context x bar phi2, then how do I interpret it? I want to say this sequent holds in that structure if the interpretation, so I will say that M models this sequent if the interpretation of this formula in context in M is a smaller subobject. This less equal is the less equal on subobjects. This is a smaller subobject than the interpretation of phi2 in M. Okay, so take a moment to digest this, which means when I'm looking at this particular thing, what does this axiom say? This axiom says that the interpretation of truth, which is the top subobject, the interpretation of truth is less equal the interpretation of this equalizer, I mean the equalizer of these two morphisms. When can that happen? That the top subobject is less equal another subobject?
It's a non-abelian proof.
What non-abelian?
Sorry.
I'm just asking. Huh? It is equal to, right? So is less equal in a poset, top is less equal an element if and only if that some element is equal to top, which means I get this commutative diagram, right? I can rewrite this as simply this, that I have M cross M, then I have M cross M, and then I have M. This is my plus M, this is my plus M, and this is the pi2 pi1 map, and this diagram commutes. This is my commutativity axiom. Okay, so something more, if I want to write down associativity, then I have M cross M cross M, then I have M cross M cross M. From identity on M plus M, yeah, and that will give me M cross M. From here I will get plus M, that will give me M. This is simply the isomorphism of different, I mean this is really this parenthesizing, right? From here I can get again plus M cross identity on M, and I will get M cross M, and here I will get plus M. So this diagram commutes is basically the associativity axiom. So you can see all the axioms, I have converted them in the algebraic setting only. I have converted them into commutative diagrams, right? The identity axiom is a bit trickier to write, but let us do that it is a left identity, let's say. So I have to start with M, then this is isomorphic to 1 cross M, and from 1 cross M I can go to M cross M, and then I can come back to M. So here I'm going to take the interpretation of the identity symbol. Let me say that. Let's say the identity symbol is M. This is E cross identity on M. This is my plus M. This is E is the identity symbol. This is identity. this particular diagram commutes, that is the statement that E is a left identity. Similarly, you can write down all other axioms. And now you know how to interpret any algebraic theory in an arbitrary category with finite limits. In particular, yeah, I mean, I will tell you tomorrow about relation symbols and all. But and how to interpret more complicated formulas. You simply have to use the more and more structure available in the subobject poset and existential quantifiers, etc. How you are doing. But some comments for which are suitable for today's tutorial as well. In tutorial, we might see some more examples like this. So if I interpret the theory of groups. The theory means the axioms of groups. Yeah, theory of groups. In first, the category of sets. What do you get? What do you expect to get? When your universes are sets, what do you get? Groups. You will get groups. To get groups. Second, when you interpret it in the category of topological spaces, what will you get? Topological groups. If you interpret it in the category of smooth manifolds and smooth maps, what will you? Lie groups. Lie groups, exactly. So these are known as internal group objects. You might have seen this word somewhere, but the theory behind constructing internal group objects is like this. All these categories have lot of content. All these categories have lot of structure, and that's why we do this. Yes. So would you not mention about? Yes, I'm going to say that. Would you not mention about the naturality and hence coherence of the isomorphisms, correct? Or the twist isomorphism? There are some problems about that in the tutorial, which is starting in 15 minutes. Yes, that this is any isomorphism. Yes. Why not category of groups themselves? And this is again a question in the tutorial, that if you interpret the category of groups, the theory of groups in the category of groups, then this is a very interesting example, as Partha has pointed out. You will get, surprise, surprise, abelian groups. So those who are interested in topology, yeah, and have studied until like higher homotopy groups, then you should know that all higher homotopy groups are abelian, especially pi2 is abelian. And then the standard argument which is used to prove that pi2 is abelian is known as, anybody from the audience?
Ekman-Hilton.
Ekman-Hilton, exactly. The same kind of argument, Ekman-Hilton argument, shows that the internal group objects in the category of groups are precisely abelian groups. Okay, so this is very interesting, and this gives the more meaning to the words. Like why it is interesting, because when you are interpreting in topological spaces, then all these maps are actually continuous, which is basically the restriction which you put. And here it becomes natural. Of course, these are all concrete categories. So you might think, what's really happening? Why are we doing this? Yeah, we can explicitly define them, but even in the abstract settings, this is really interesting. I will tell you tomorrow that you can even interpret natural numbers object in some categories using simply finite co-equalizers. Right, so there is a lot of potential here, which you cannot see in just the categories of models in sets, in the category of sets. Any questions? Like, I'm not going to say anything more new.
The first diagram,
Uh-huh.
if we have to show commutativity, wouldn't we have m cross m, then pi1, pi2, m cross m, and then plus m to m?
Yes, I just ate up that identity morphism. It's a commutative square, but I ate up the first pi1, pi2.
Okay.
Well, you are right that I should add here m cross m, and then this should be pi1 comma pi2. This is technically the correct one, and then I should add plus m. Yes, that's true. But because it was identity, I already mentioned that I ate up. Yes. So any other questions from any audience? We will discuss a few more examples during tutorial. And yes, Anna, you want to say something? Okay. So we'll meet after 15 minutes.
Yeah. So if you are not having any questions right now, you can later on email Professor Kuber. And so now we'll be having a tea break for 15 minutes and we'll come back with the tutorial on stone.
On
Syntax
semantics dualities and some category theory as well, because that is the basic thing. And I think, yeah. So is it Professor Partha Ghosh?
I'm still, I'm in UNISA, University of South Africa.
Yes. So can you tell me, is this your research area?
Yeah, I work in category theory.
Okay. I'm very glad to see somebody who knows these things.
Yeah, I am actually trying to internalize the notion of a space inside a finitely complete category with co-products and factorization structures.
Okay. By space, you mean a topological space?
Well, yes, I have started with internalizing the notion of a neighborhood system.
Okay.
And that gave rise to many interesting observations.
Right.
Yeah. So.
Okay. Now, I'm really glad to see somebody who can talk about these things, because our purpose of this school is to increase awareness, and the kind of coherence conditions, etc., that you're talking about, we can't really address them directly because most of these people have just started learning category theory from Monday.
Aha, yes.
Yeah, so we gave 3 basic lectures on category theory, like starting from the definition of a category. And on the 5th day, they are looking at categorical semantics. Which is torturous, to be honest, but that's the purpose of the school anyway.
Yeah.
Yeah, that's why we are not doing a lot. Like the exercises will still contain that if you have products and equalizers, then you can construct pullbacks and that kind of thing.
Okay, that's good. Yeah.
Yeah, thanks for coming.
Thank you. But where are you from?
I'm from IIT Kanpur.
Aha, okay. Good. And you work in?
Currently I work in representation theory of algebras. But yeah, my long-term interests include category theory and model theory.
Yeah, that's good to know. Yeah. Thank you.
I changed my topic because I couldn't find any students interested in working in these topics.
Yes.
In India, like you are probably aware that people don't like category theory. And it's the situation in most parts of the world. They call it abstract nonsense. And similar is the situation with logic. And
yeah, you see, the problem is it is a new, although I believe that category theory was there from the first day when mathematics was started,
Mhm.
but it was formalized only in the 60s.
Yes,
The paper by MacLean and Eilenberg,
Eilenberg.
and
Yeah.
it is still quite new, so people don't really like to give it a position, which is obviously the case even in every human society. You don't like someone outsider. So yeah, but that will be very soon, I believe, taken over, because another thing is that possibly we can blend our set theory courses with a little more categorical imperative. And that will be a better introduction to category theory instead of starting off
So
with.
if I may say so, that we don't even have set theory courses.
Is Mohua not there?
No, in IIT Kanpur we have.
Yeah.
This is, I mean, that is what she pointed out during inauguration of this school, that IIT Kanpur is one of the very few maths departments offering, yeah, and probably the only offering a compulsory course on set theory and logic.
Yes. So that's why I asked, is Mohua not there?
Yeah, she's there. She's here.
Yeah. So, yeah, so set theory. Yeah, that's another issue. Axiomatic set theory, I believe, is rare. I think in ISI only Srivastav used to give
Correct.
it, and
Correct.
after that nobody.
Correct. That's true.
Yeah, so that's also a problem. But well, set theory is only given in South Africa. It is in UNISA and in Cape Town, where there is George Janelidze.
Okay. Okay.
Elsewhere, it is not given. So set theory, category theory is much more, but set theory even it's not given.
Yes, that's true.
Yeah.
And that's the plight. What can we do? We are just trying our best to raise awareness. If in future we can find some students interested, then I will get back to it.
Yeah, that's quite nice. Yeah, but we'll have to face it. There's no questions about it.
Yeah.
It's a new subject and it's a new area. So, well, we'll have to face it.
Correct.
Yeah.
Yeah. Thanks. It was nice chatting with you. We'll
Thanks. Nice chatting with
hope
you.
you
Too.
will come back again tomorrow.
Yeah, I'll come. In fact, I was out of town and that's why I couldn't join earlier. But I'll come back to Nick's talk also.
Sure.
Yeah. And if you don't mind in the tutorial, I might be there also.
Yeah. Please be here. Generally, people run away during tutorials. That's why I didn't say anything.
Yeah. No.
Okay. Thanks a lot.
Thank you.
Hello, hello. Yes. So the survivors will do the tutorial. There is very few. And we have shared in the chat what is the tutorial sheet. Maybe I should open it and share it as well on the screen.
So there is an access issue with the link.
There is access issue.
Yeah.
Okay, he's updating. Now it's done. Please try it again. Click on the link.
Yeah, it's working.
Good. Can offline participants read this font? No? He's saying no, you are saying yes. That's weird. The person sitting in the back. Oh, you said yes.
I'm sure it's fine.
Fine. Yeah. So please try the first one. Today is a longer tutorial. We might talk about a few things, but I don't want to start with anything new. Please try the first exercise. This is really easy. Show that pullback of a monomorphism is a monomorphism. Oh, if anybody has any questions, please ask me. Yeah, I'm around.
Did anyone try the first exercise? I mean, that's the most natural thing. You try the first one. But first of all, let me ask them what they're thinking about. I hope the question is clear because it has been stated so many times during the lectures. So just remember, to show that F prime is a monomorphism, you have to check what condition. So just impose the definition and try to check the condition. Hint should be universal property or pullback.
Please, can I call names now? Debanjan, are you trying anything? Sujit,
Yes, I'm trying.
have you got the solution, Debanjan?
Actually, we have to explore the idea that if itself is a monomorphism, and if we introduce two maps from C like that, we have to do that.
Do you have any way of writing on the screen?
Unfortunately, no.
Okay, so can you guide us through the diagram? I'm going to write something on the board. Where is the chalk? Good chalk, yeah. I'm going to write something on the board. Please guide me. Let me write ABC. This F is a monomorphism, and then you have G prime and F prime. Yeah, how should I start? How should I start? Am I audible, Devanjan? Hello? Hello?
Yeah, you can take two maps to D
Two maps from where to where?
from some object to D.
Some object to
D.
P, correct. Okay, good. So I can take D object and then I can take two maps A and D from here. And what should I assume?
Such that their composition with F dash is are equal.
Correct. F dash A is equal to F dash B. Now?
Yeah, so these two maps are actually giving you a map to C from that's which
Correct.
what is the symbol for that
So,
object?
yes, so this is F dash A is equal to F dash B. Good.
Yeah, and that will also give map to A. Two maps to A.
Yes, these will be two different maps to A.
But they will be equal since your F is monomorphism.
Correct. So G dash A and G dash B. But since this whole diagram commutes.
Yeah, you have unique map to D.
Yeah, why will this whole diagram commute? So I'm writing this, yeah. If F G dash A is equal to F G dash B, then I can conclude that G dash A is equal to G dash B.
Yeah.
Yeah, is this true?
Yeah.
Because FG dash A is precisely. So we want to show this, yeah? So FG dash A is precisely GF dash A. And this is given to be equal to GF dash B, which is equal to FG dash B. So by transitivity of equality, we have got that these three morphisms are the same.
Yeah.
These two morphisms are same. And here and hence G dash A is equal to G dash B. Now what? Now tell me how to finish the proof. Anyone?
Since P is the
Yes,
as
P
in,
is
because
what?
of the limit property.
Correct. Since P is the pullback of this
Pullback, yeah.
diagram, it's a limit, which means universal property. So this outer square is commutative, the inner square is commutative. So this cone must factor uniquely through this to the limit cone, and therefore there cannot be two distinct, so they have to be equal. Okay, good. So by the limit property, universal property of the limits, we can get that these two are equal. Well done. So what is the second question now? Yeah, show that the categorical product is, so try the third one first. For any two objects A and B, show that A cross B is isomorphic to B cross A. As sets, you have done this several years ago in school, perhaps, that these two are in bijection with each other, but now you simply have to do the same thing in categories.
Because of pullback, there will be isomorphic.
Because of pullback, they will be
Isomorphic to each other.
Where is the pullback?
So A cross B will be the pullback of A and B.
A cross B will be pullback of A and B.
Similarly, B cross A.
A cross B is B. No, there is no
cross
pullback
product.
here, Vargo.
It can be considered as pullback over terminal object if it exists.
Right. Yeah. Who
It's
was
not-
speaking?
It was
Yeah,
Sujit.
me.
So you're not given that you have terminal or
Yeah, that's why we can't use it.
yeah. Do not get into that. Just try using universal property of product. Like that's all that you were given.
Yeah, that's what I was saying. So A cross B can be treated as the product of A and B.
Yeah, that's what it means. A cross B is the product.
So then, so that's why B cross A will also be the. So that's why there'll be isomorphic.
Any two products are isomorphic, right?
Yeah.
Yeah. So this is the product diagram for, this is the limit diagram for, so given any D with a pair of morphisms, there exists a unique morphism such that both these triangles commute. And what is this morphism called usually? This is called F1, F2. Yeah, you have to give two different components. It is F1, F2. For B cross A, you can say that it's the other way around, F2, F1. And you will have pi2 and pi1. So this whole diagram taken, this A and B will be fixed. Here we will interchange. Yeah, you will have pi2 and pi1, and the same thing will happen. And because we have shown that products are, or any limits are unique up to unique isomorphism, so A cross B and B cross A will be naturally isomorphic. Okay. I think you can, those who know something about rings, yeah, those who have seen that, can you try the question of inclusion from integers to rational numbers? This is a very simple question, that this inclusion, which I'm going to denote by I, this is an inclusion, which means an injective function, and injective functions are monos. Yeah, that's a very standard exercise. You can check that. You do it element wise, and therefore you show it they are monos. But now the surprising thing is, this is also an epimorphism. So please try to show this proof. Okay, just to give you a head start, what do we need to start with? What is the definition of an epimorphism? Correct. So we have to start with a pair of maps to another ring, let's say R. And what is given to us, read this properly. We are given that f of x is equal to g of x for all x in Z. This is given, and you have to prove that, I mean, let me call this n, that will make more sense. And you have to show that f of p by q is equal to g of p by q for all p by q in rationals. This is what you have to show. Can you see that the property of epimorphism is simply about the image determining, the image of I determining what happens next? That is the underlying idea. It has nothing to do with being a surjection. If I know my ring homomorphism from rational numbers, if I know its image on integers, then I know its image on the whole rationals. That is the idea here. So now, of course, I mean, category theory is just a language. You have to use the properties of rings and ring homomorphisms. So here I am assuming that all ring homomorphisms do preserve identity, addition, multiplication, zero. Yeah, everything is being preserved. Now try to finish this. I'll give you 2 minutes. Any answers from the participants? Multiply by q on both sides. Very good. What will happen? If I multiply by q, q times f of p by q, what will happen? Yes, q will go inside. This is f of p. Very good. This is f of p. And then yes, and then what? We can divide by on both sides. Do you know you can divide by q in R? You have to define it. You are forgetting that. How is f of p by q defined? See, you simply have to use this. It does satisfy this property because of ring homomorphism. So if this has to be defined in this way, which means it is determined by the image of f on integers only. Yeah?
It should be f of p by f of q, no?
F of p by f of q, no. No. Any questions or doubts about this? Anybody trying some other exercise?
Why it is not f of p by f of q? Like, it is a ring homomorphism, no?
Sorry, who is this?
Sujit.
Sujit.
So if p is taken to f of p, so 1 by
do it. Yeah, you walk me through it, I will write it.
So P by Q can be written as PQ inverse. And
Sorry, I think multiple people are talking. No zero divisors. Yeah. We are not putting any restrictions on R so far. Yes, somebody else was also talking apart from Sujit.
Yeah. No, I just pointed out that like even I think that f of p by q is fp by fq, because p by q can be written as PQ
Sorry, can you
inverse,
be a bit louder?
this
Animate. Is volume low?
Okay. Is it better now?
Yeah, please talk.
Yeah. So I was saying that f of p by q is the same as fpq inverse, and this splits as fp times fq inverse. And since this is a homomorphism, this is fq inverse is the same as fq inverse.
F of q inverse, yeah.
And this is the same as fp times fq inverse. Like yeah, since it's a homomorphism, and this is fp by fq.
f of q inverse is f of q whole inverse.
And where will this f of q whole inverse, and then
yeah, so that's how we write like f of p by f of q, na?
And then what will you do with G? G will also be similar.
Yeah, G will be similar, and we know G and F both agree on P and Q. Both are integers, so their quotients will be equal.
I was using this idea. So if I take f of p by q and I add it q many times, then that is same as q times f of p by q. I can take this q inside. Just using addition, I'm not even using multiplication here. Say it loudly. Yes. F of q inverse will not be f of q inverse. Why not? Yeah. Oh, but f of 1 is 1. They are not equal. I'm also confused now. Division by q is not the?
Division by q is not a multiplication by some element of R. Division by q is the inverse process of multiplication of q times addition. So that is some different process, and multiplication by fq inverse is some different process.
Yes, they are different.
That is what is causing some confusion.
Yes.
The similarity in notation by integers and the similarity of notation with elements of multiplication with elements.
Right. So we need divisibility condition.
But Q is a field, and like its image will also be a field. So
Yes.
FQ will be invertible.
Somebody speaking? Yes.
So Q, the field of rational numbers is a field, and hence its image will also be a field. So f of q that we are considering will be an invertible element in the image in the codomain.
Okay.
So we can cancel.
Nonetheless, if f is a ring homomorphism,
Hold that mic.
Oh, yeah. So nonetheless, if f and g are ring homomorphism, this properties hold, and this is precisely f of p by q. And on the other hand, you have g of p by q is g of p, g of q inverse. Now, since on all integers they're equal, you have that f of p is equal to g of p, and f of q is equal to g of q, and so is their inverses.
Okay.
And therefore, these two are equal, which means these two are equal, and that is the requirement. Right?
And what is the problem with the other approach? It is a ring homomorphism.
Yeah. No, if q has an inverse, then
so the proof for that
right?
is this. Yeah, f of q times q inverse is equal to f of 1 is equal to 1.
No. If at all q has an inverse, then f of q is going to have an inverse.
So this is 1. Yeah, multiplication is 1. No, that won't happen. These are ring homomorphisms preserving unity.
If q has characteristic, q is characteristic 0, the power must necessarily have a characteristic 0. There are no.
Yeah.
Therefore, you can subtract q times f of p by q minus g of p by q equal to 0. Q is not equal to 0. Therefore, f of p by q equal to 0.
No, sorry, I didn't get you.
No, the R cannot have a characteristic 0.
Or cannot or should. Right.
So therefore, Q times f of p by q, you write down f of p by q,
Huh?
times f of p by q, q times.
Yeah.
Q times is equal to f of p, starting point here.
Yes.
Which is equal to g of p.
Yes.
Q times g of p. Which is same again, q times g of p by q.
Yes.
Therefore, q the subtract one from there because read q times f of p by q minus g of p by q. Q times f of p by q.
Yeah, that is also
G of p by q
the same
equal to
side.
0. Because it has no zero divisors, therefore f of p by q is equal to g of p by q.
Last operation is not a multiplication. Huh? It's last term is
Yeah, that is q times 1 actually.
This q times.
No, that is fine.
Yeah.
So
But we are still assuming that R is an integral domain anyways.
R has no zero divisors.
Yes. No, I mean it's the same thing.
R is just a ring.
R is a ring because if they are mapping from Q to R, then we cannot have a zero divisor.
The image of Q in R will not have
Yeah,
zero divisors.
that is
That's
true.
true.
Yes,
That is
that
true.
is true.
That's what we are.
Yeah.
That means that we can remove this Q.
Right.
No, but it's again the same thing what you did. Like,
multiplication like Q is not an element of R.
No, this
but
is
that's
so
the
taken
idea.
it so many times. It's divisibility condition.
There is Q into 1.
It is divisibility condition. Something times, like something added to itself Q many times is zero. No, that is characteristic. Like
Even without going to characteristic, this still holds, right? There is no problem in this as well.
I feel both the proofs are correct.
Of course.
No, because what is f of Q inverse?
No, if Q has an inverse, then f of Q is going to have an inverse.
This is true. F of Q times Q inverse is f of 1, which is equal to 1. Because it is a unital ring homomorphism, and therefore, so both the proofs are correct. And
No, first one or second one is showing that it is no zero divisors.
right.
Correct.
But no zero divisors follows from the fact that the image is a field, and like fields have no zero divisors. I think that's how we are getting that the image has no zero divisors.
The image has no zero divisors, correct. Right.
So in the hard part, you have another exercise which is similar to this, which says something about show that. So it's question number 16. If you
Speak loudly in the mic.
In question number 16, in the hard part, you have a similar exercise. You may wish to have a look at it, which is about monomorphism in the category of divisible abelian groups. So these two exercises are to show you that though we define monomorphism by saying that, oh, you're trying to generalize injective morphism or epimorphism by generalizing surjective morphism from the category of sets. But now you do see that there are categories where these two notions do not coincide.
And for those who are not very familiar with this, that problem is indeed hard because it uses several exercises before that.
Maybe, but one can,
But before that, like let's say, can you first prove that an isomorphism is both a mono and epi?
Yeah, this is question number.
This is a trivial question.
This is
but try to do it.
Question number 7.
Nevertheless.
Proof question number 7.
And if you follow that every isomorphism is both mono and epi, the converse is not true. Yeah, so please pay attention to this morphism. Because this is injective, it is a monomorphism, and it is also an epimorphism. We just argued about it. So it is both mono and epi, but clearly it's not an isomorphism. Yeah, there cannot exist an isomorphism between a field and a ring that is not a field. So which means there are morphisms which are bimorphisms, both mono and epi, but which are not isomorphisms. If at all monos and epis, like bimorphisms, coincide with isomorphisms, then we say that the category is balanced. Yeah.
In this analysis, can you show Schroeder percent? It may not be Schroeder percent. But this is from A to B is such that can be any other map like this. Say that. So these are any. Maybe you should draw. Yeah, using the ring structure. For 1 for A plus B. In the category of rings. No, this is bad, but that is the one you have to construct the U prime, right? And then
yes, that's what said. So in which category that is talking?
In B cross A. So this is the U prime. And this U prime is coming from I don't know. Yeah, because of universal properties. So by U prime I can write.
I'm thinking about something which is similar to that. So the question that Professor Adimurthy is posing is, can we prove something like, or what is the categorical analog of Schroeder-Bernstein theorem? If anybody in the audience has any idea, please contribute. I think I have seen something similar in topos theory. I don't clearly remember. You need lot of structure even to talk about something.
Excuse me?
It uses elements, and that's why, yeah, it uses elements and we don't have elements. So that's why you need lot of categorical structure to.
Excuse me?
Yes.
Well, the fact that Schroeder-Bernstein theorem is equivalent to the fact that every epimorphism is split.
Yeah,
and
that is axiom of choice.
And this is actually axiom of choice.
Yes. Axiom of choice we can interpret in categories which are sufficiently complex.
No. Actually, equating large classes of so there is a whole gradation of epimorphisms starting from isos. So isos, then split, then regular.
Yeah.
Then you have all those pullback stable ones and so on, going up to extremal, strong, and finally up the ladder to epis. Now, so axiom of choice will be, or any variation of it would be equating the epimorphisms to a special kind of epimorphisms.
Yeah. There are
so epimorphisms equal to split epimorphisms is precisely your axiom of choice.
Yeah.
Yes.
There are several non-equivalent versions of axiom of choice, which can be interpreted in different classes of categories.
Yes.
But I mean, I'm still confused. Like, how is that the state? How is that equivalent to Schroeder-Bernstein?
Schroeder-Bernstein's theorem says that if F is a monomorphism,
yeah, from A to B,
yeah, and G is a monomorphism from B to A,
yeah,
then there exists F and G are both bijections, right?
Yes. No, F and G are both bijections is not correct. There exists an isomorphism.
Yes, there exists an isomorphism, but then monomorphisms are same as, so this can be equivalently stated that if F is an epimorphism and G is an epimorphism, then there exists a bijection.
No, this is totally different statement.
If F is an epimorphism, then there exists a right inverse of F, which is F prime, a monomorphism from B to A.
These are different statements. This is only about comparing cardinalities. Schroeder-Bernstein is about comparing cardinalities, and every epimorphism being split. That has to do with axiom of choice. That is independent. I don't still see the connection between this existence of monomorphisms in opposite directions and existence of an isomorphism.
Yeah, you're right. I'm trying to formulate it.
It doesn't. Yes, you are right. Schroeder-Bernstein proof doesn't depend on our axiom of choice.
So why are we relating it to
Yes. I made a mistake. Yes.
Yeah, these are two independent things. I'm asking whether we have seen something similar in this context in category theory.
Locally, finitely presentable category may have something like, at least you need to interpret finite objects, right? Or
yes,
cardinality sorts of things. So
yes,
finitely presentable category or things like that.
I will talk about it briefly tomorrow. I have many things to do tomorrow.
In toposes, there are some.
I know in toposes you have something like Schroeder-Bernstein, but I cannot pinpoint it. My memory is too old right now.
Even I cannot remember now.
Yeah.
Anyways, question are we looking at now?
Yeah, we should look at some other question as well. Yeah, everybody should get something out of this. So has everybody finished proving that every iso is a mono and epi? But we have seen an example that mono plus epi doesn't imply iso. However, if you put a slightly stronger condition that I have a split mono plus epi, then this implies iso. Please try to prove this. These small exercises will help you to get used to the categorical language and how morphisms work. Yes, what is a split mono? So a monomorphism is split if there exists a G such that G composed with F is equal to identity. That's a split mono. So this will show you that being a split mono is much stronger than being a monomorphism. However, in the category of sets, they are equal.
Yes, you actually need some kind of cardinal objects and sub-objects to be classified by them.
Classified by cardinal objects, what do you mean by that?
Yeah, that means every sub-object is equivalent to some cardinal object. Now, what is a cardinal? A cardinal
is simply a bijection equivalence class of ordinals.
Yes. Now, that's how would you bring in the ordinals? The ordinals should come in as
generally, like in accessible category theory,
yes, in accessible,
take this as some external object, like cardinality is an external thing, and then you associate to each object a presentability, which is a cardinal number.
Correct.
But I don't think that still connects it back to Schroeder-Bernstein. I don't have this book on me right now, but I think categories for this sheaves in geometry and logic by Macklin and Mordyke might have some lead about that. Any offline or online participants who have finished this proof, split mono plus epi is iso?
Yeah.
Yes. Please tell me.
So one side it's already given that you have identity on A. The other side we need. So we take two maps from B to B.
Two maps on?
Map from B to B.
B to D, okay?
B to B, sorry.
B to D, right?
Not D, B.
B to B itself?
Yeah, yeah.
Okay.
The one is identity on B and other is F composed G.
Okay, F composed with G. Correct?
Yeah, so because this is epimorphism and these compositions are equal.
Very good.
So these two maps are equal.
So from B to A, right? Here.
Yeah. Let me think again.
Yeah.
No. I'm using property of epimorphism.
Yeah. Oh, F is
epimorphism. So the opposite diagram. Yeah. Yeah.
I mentioned yesterday I'm bad with left and right, and you saw that.
Yeah. F composed G.
Yes, F composed with G composed with F, you will get, yeah, these two morphisms are equal. So therefore you'll get that identity on B is same as F composed with G and you are done. Good. Right, so this was an easy exercise now. Fifth one is really easy. Yeah, fourth one you can do yourself. Now let us go to something that is more interesting. I don't want to talk about kernel pairs yet. Where are those questions about? Yeah. Try 13. It's not really hard. I don't know why Deepankar put it in hard. It's not hard.
The list of hard exercises was too small. So
it is meant to be small. Yeah, even if it is small, it's meant to be small. Can you please focus on this board? Okay, so try number 13. Yeah, that is really interesting problem.
focuses on one.
So actually, the definition of a limit in general, yeah, that definition is sufficiently complicated and abstract. And that's why we only talk about certain spatial classes of limits. This is meant to be a crash course on category theory. So that's why we avoided talking about the abstract definition of limit. But then whatever classes we dealt with, whatever classes of limits we dealt with, like pullbacks, equalizers, terminal, products, so those are interchangeable. I mean, given some of them, you can construct others. So for example, this one is if and only if, right? So if you have a terminal object, this is the hint. If you have a terminal object, then there is a unique morphism to the terminal object. Now, the way I have drawn this diagram, what does it complete to? Lavesh? Pullback, yeah. What will be the pullback of this? Product of A and B, yes. Now, can you show that this is precisely the product of A and B? That's your claim right now. You have to finish proving that.
Hello? আমি তো পাঠিয়ে দিচ্ছি নাকি?
Can you finish proving that? Okay, this is 14, he's pointing out. But for me, all of those questions are equivalent. 13 and 14. Given some limits, you can construct other limits. This looks like graph theory, very simply put. What is the definition of a product? Nupur?
If we can show that this satisfies the universal property for the product, then we've shown that it's isomorphic.
Exactly. Whenever I have these two legs of the cone, then there should exist a unique one. And I'm not given this part. That is the universal property of the product. If I'm not given this part. But even if I'm given this part, then what will happen? Does this outer square commute? It should, because one is terminal. Which means outer square commuting is not a restriction at all. It automatically commutes, and hence you have a pair of objects, and by the pullback, universal property of the pullback, you have a unique map such that these two triangles commute, which is precisely what you need for making it a product. This part is superfluous. You don't really need that. So from pullbacks and terminal, you can construct products. Now from pullbacks and terminals, can you construct, or you have already constructed products, can you construct equalizers now? From pullbacks, equalizers, and from pullbacks and products, can you construct equalizers?
Okay, so Partha Pratim Ghosh has suggested a paper where something is found. The paper says that you can define something like where you have monomorphism onto different, like going in different direction. So he has shared a link, but such categories are not really every category. Yeah, so this is
okay.
Okay, so this is a category where you can expect, but no example is given, I guess.
No, so I can only say something about this, that every category concrete over finite sets. Yeah. So we haven't defined concrete categories in our course yet. So let me do that. So a category C is said to be concrete if there exists a functor f that is faithful. So I think in hurry, Deepankar did not distinguish between full and faithful. So let me remind you quickly. So faithful means whenever I have home CAB and I have home C FAFB, then this map being injective, yeah, F mapping to FF, this map being injective is faithfulness. This map being surjective is fullness. Fully faithful is bijection. Yeah. So if there exists a functor down to the category of sets which is faithful, then you say that the category is concrete. And what that paper is trying to say, that a category which is faithful, which is concrete over the category of finite sets, which means here you have to put fin. A faithful functor down to finite sets that satisfies Cantor, Schroeder, Bernstein, but I don't really find that interesting given that it's just about finite sets. I think there would be something more interesting for even category theoretically it's difficult to do as well, to talk about cardinalities. It's not a concept that is inherent in categories.
So then ordinals also is not
Hmm?
Ordinals also is not.
Sorry? Cardinals, yeah.
Ordinals.
Yeah, we don't. No. We can define a well-ordered set in a category because no, not using Zorn's lemma. Let me think about. No, we can't. Unless or until you have, you can interpret higher order logic, you cannot interpret ordinals. Because the definition of a well-ordered set says that every non-empty subset of it has a least element. So that means you are quantifying, Purvita pointed that out in her lecture, that when you are quantifying over subsets, that is higher order logic. If you are quantifying over elements, that is first order logic. Yes.
Quantifying over subsets is quantifying over elements of the power set. So
yes, but at a time you are only given one domain of discourse. You don't have access to its power set when you are dealing with a structure. When you are dealing with a group, you don't have access to the power set of a group. By definition, you only have access to elements of the group. So unless or until you want to deal with pairs, that x comma power set of x, you can't have access to elements of the power set. You are right, but that is higher order logic.
In set theory, we take power set because of the axiom that power set.
Yes. Even in category theory, you can have exponential objects or power objects in topos theory. So you can deal with them. You still have this belonging relationship between elements and subsets and everything nice happens there. However, you can interpret higher order logic in toposes. So the meaning is still the same. Quantification over elements of the domain is first order. Quantification over power objects or elements of the power set, that's higher order.
So Vinod is asking if problem 10 has been discussed.
No, we haven't done it yet.
We are still doing category theory problems.
Yes, I haven't. I mean, I have given these exercises 10, 11, 12 just to make sure you do something about stone duality, read something about stone duality again. But yeah, I mean, after pullbacks, terminals, and products, do you know how to construct equalizers? If I'm given this kind of diagram, right? A and B with F and G. I know how to construct products and equal pullbacks. Can I construct equalizer of this? Okay, that's a start, and then Now this is what this is a trap. Yeah. If you take this and you take H and K, then these H and K need not agree. Yeah, this is the interesting thing. They don't necessarily agree.
Moreover, if that were the case, I wouldn't have defined two different things.
Any other idea? A pair of maps is a map to where?
First take the product.
Product of what? Yes, there are so many things possible. A and A. If I take a F and G. F and G product will go from where to where? Is the camera focused on this board? Yeah, F and G will go from A cross A to B. Think about products, yeah? Whenever you have a product, then you can post compose it with projections and then you get something useful. But that will be only useful if your target is a product. So if I take B cross B, then I have a morphism called F comma G. Yeah, this is okay. But this one, maps from products, they are not helpful. Maps from co-products are helpful. Maps to products are helpful. Huh? Disjoint union. No, you are only given terminal, pullback, and products. You have already constructed products. See, this is the hint. You have the diagonal map here. 1B comma 1B, this is a mono. Now you construct a pullback. This diagonal map is clearly a mono. You can verify that. This is a mono. So pullback of a mono is mono. So this is a mono. So I have already got a mono such that the diagram commutes. What does this mean? Let me call this map E and let me call this map H. It means that GE comma FE, I mean FE comma GE equals H comma H. So this H is nothing but FE equal to GE. Right? This is FE equal to GE, which means we have the condition necessary for being an equalizer. Yeah, I'm given this P. First condition for being an equalizer is that FE should be equal to GE, and for any such D and a map K such that Fk is equal to Gk, we have a unique map factorizing through P. For that, use pullback property of that square. This is a very clever idea to convert one kind of limits into another kind of limits. Since, I mean, those who are new to this, they should actually write this down to understand it properly. Yes.
Amit?
Yes.
Would it not be nice to say that limits have always been considered in mathematics and in a much more elaborate way as good subobjects of products, and vis-a-vis colimits as quotients of sums?
Yeah. Yeah,
So,
that's true.
So that's a much more intuitive idea of limits and colimits.
Yeah, for example, the pullback of any diagram that's true. I did not use this notation, but usually it's said to be, the pullback notation is this: A cross C with a subscript B. This means that we are choosing those elements from those tuples from A and A cross C, which become equal after getting to B. And that is the intuitive idea from sets. So what he's saying, there is a much more general result that any limit can be constructed using only products and equalizers. He's pointing towards that result.
But
It
we
says,
use, but we stated that as our definition, that our limits.
Yes. In this course, we have stated that as definition. But you can construct a massive product, and then you can construct one equalizer, which will give you that. So it is all sub-objects of a massive product. All limits are sub-objects of a massive product. Whereas all co-limits are quotients of a massive co-product in general. Co-product is sum, and here it's product. So that is the general idea of limits and co-limits. Okay, so I think you can try number 13 yourself. For 15, you may want to just refer to the Wikipedia page of Ekman-Hilton argument. Yeah, that's an interesting thing. 16 is hard.
Not really.
I mean, if you know Yoneda.
Not even that. If you know what divisible abelian group, you may try that. Just the definition should help you. Like, it is not that difficult.
Does anybody want to say anything about 10? So yesterday I said this in the class, that if S is a consistent theory, then you complete that circle. Yeah. From theories, you go to models, and then from models, you find out the common theory of those models. Then that is a deductively closed theory, which means all its logical consequences are already present inside it. So does anybody? Yes.
So by definition itself, the theory is deductively closed, right? I mean, I don't understand what is there to show.
No. I did not take that as my definition.
Oh.
Is it Vinod?
Yes.
Yeah, Vinod. So yesterday's lecture, you were present?
Yeah, I think I don't remember this particular part.
Okay, so I said that a theory is simply a subset. It is a subset of the set of formulas that cannot deduce a contradiction.
Okay, that's how you define a theory.
Yes.
Okay.
So do you mean that on the categorical side, are you taking a theory to be a category with finite products?
No, I mean, yesterday I did only this propositional theory. So there I did not say anything. I just took it as a set. I wanted to do a toy example of syntax semantics duality. That's why I did not say much. Only a collection of formulas with subset relation. So I established an antitone-Galois connection between subsets of the set of formulas and subsets of the set of valuations. Yeah. Any questions? You people look confused. Suyash? You have done a course on logic already, yeah? This should be easy.
So that suppose a statement can be proved in S, so every model, so it is shown in every model of S.
Yes. So suppose S proves alpha. Then for all V modeling S, we have V models alpha. I mean, these two are interchangeable. Yeah. Then right. It means that it is the common theory of all the models, all the valuations which satisfy, all the formulas which are true in every model. Well, this is precisely what we have. Therefore, alpha belongs to theory of V for all V modeling S. Therefore, alpha belongs to theory of models of S. Correct. That's the simple proof. You're done. Yeah, if alpha is a logical consequence, then alpha belongs to this. That is the meaning of deductively closed. Right. And these two are also, yeah, the example 12 is a bit more involved. What we are trying to say, so what we are trying to say there is that duality actually maps good subsets to good subsets. Yeah, yesterday I did not mention that, but Nick mentioned this in his talk. Yeah, that homomorphic images of Boolean algebras, they correspond to closed subspaces. And inclusions, I think, correspond to open subspaces of stone spaces. So I'm asking you to prove one of them. So the deductively closed consistent theories, they will correspond to closed subspaces of this, non-empty closed subspaces. So I'm going to extrapolate something now, looking at the faces of all the offline participants and the way they are interacting. They are absorbing something, but not necessarily in its full capacity. I'm sure that is similar with all the online participants as well. And this is very natural. In an intense school like this, you cannot really take in everything. Yeah, I always like to give this kind of analogy. If you go to a museum and you look at a painting, then in that painting, you won't necessarily be interested in locating a particular pixel in that painting and figuring out what color there is. You try to get an overall idea of what this painting is trying to say, the broad shapes. Lots of it is black boxes. Yeah, those different, unless and until you have more time, you won't really go inside the details. You just like, okay, this painting contains a house, there are mountains, there are trees, and that's all. The general perception is that the colors are bright or the colors are dark, whatever. But only the general perception is what we perceive when we look at it for the first time. And that is precisely what such schools are meant for. You should get a general feeling about the subject, and that is where the teachers come in. Otherwise, there is no purpose of teachers. You can only read and read and read. The idea to stand here and deliver lectures is not just to pass on the definitions and theorems. It's also to pass on the philosophy behind the subject. If at all, some of you get interested in this topic after this school, you can spend more time. You will invest more time in learning these topics, and you will have some guidelines that you know where the subject is going to go in the future. And then you will try to fill in the details. Oh yeah, I remember something was said in that direction. That's a discrete jump. You had to fill in that in a continuous manner. So always try to take in the broad ideas and then fill in the details. Right. On that note, I mean, I will leave exercise 12 for you. I still have some time and I would like you to try the theory of equivalence relations using sequence. Yeah, this is not hard, but this is this hands-on experience will be really useful for tomorrow's lecture. What are the defining properties of an equivalence relation? Symmetric, reflexive, and transitive. Very good. Try to write down the axioms in the sequent language.
Sequent language as in the M cross M, that commutative diagram.
No. Sequent language is not using universal quantifiers. That sequent, single turnstile symbol. You have to set a context, and in that context, you have to write down these axioms. And you have to do it in a minimal fashion, yeah, not using very complicated formulas or strong formulas. What is the axiom for reflexivity? X is equal to X. Sequent X is equal to X. I mean, how will you write it as a sequent?
T in the context of X, X is equal to X.
Correct. Yeah, a tautology entails in the context X that X is equal to X. Okay, go ahead, write down symmetry. Oh, sorry, not X is equal to X. I should have said EXX. Yeah, this is a binary relation symbol, EXX. And where is the sequent? Huh? Yeah, I mean, this is okay. This is XY. That's okay. Then what should I write to the left? What should I write to the left of it? Do you need if and only if?
EXY arrow EYX.
EXY arrow. Okay,
EYX.
okay. And what is here? What is to the left hand side?
Green.
Once again, I can put T. Right? It is always true that EXY implies EYX. But this is very heavy in the sense that it uses implication. So that reduces the class of categories in which you can interpret it. Now replace that implication by this single turnstile symbol. So this more simpler one would be whenever EXY is true in context XY, then you will have EYX. The sequent notation, like the single turnstile, is playing the same role essentially. It's implication, if then. And for this, like the interpretation will be that interpretation of this will be a smaller subobject than this. However, the notion of implicate, the interpretation of implication in a category is usually iting implication. So it's not the same understanding. Okay, what about the last one? Very good. EXY and EYZ entails in the context XYZ, EXZ. So now can you tell me what kind of what fragment of first order logic, in what fragment I can express these axioms?
Horn sequence. Horn.
Horn, yeah. I am only using truth and conjunction and nothing else. Right? So this is one of the important observations, that in Horn you can express an equivalence relation, you can express a partial order, antisymmetry can be expressed. However, you cannot express that a structure is a linear order in a Horn fashion. Because what is linear order? It says that it has a trichotomy result. Or if you are using less equal, then it has a dichotomy result. That either x is equal to y or y is less equal x. So you have to use disjunction. Right? So you can interpret it in coherent logic, coherent categories, but not in Cartesian categories. Right? So you will start thinking about things in a different way. The purpose of doing logic is almost never to like prove big theorems. It's about, it goes backwards. Yeah. Our brain already processes lots of things, and we just have to understand how and how we can formalize it. And so try to go backwards and write down different theories. And I'm not going to give an answer to this. Yeah, this is I'm not asking you to like interpret all these axioms. I haven't even told you how to interpret relation symbols and formulas involving relation symbols. But the question is, what is a model of the theory of equivalence relations in the category of abelian groups? So think about it. And any questions today? Online participants, any comments or questions?
Well, just one.
Yeah.
Hello.
Yeah.
Yeah. Just for one of the hard problems, you mentioned a Wikipedia page, right? What was that?
Yes, that is Ekman-Hilton theorem. Let me put that in the chat. Ekman-Hilton argument, sorry. Yes, Professor Partha, you want to say something?
No, I said that your idea by this logical propositions was quite fascinating, of internal equivalence relations. I usually go in the more categorical way. Yeah. Good. Yeah.
Yeah.
Thank
you. Okay, so I think we'll stop this session for today. And I will lecture tomorrow again. That is the only lecture. And after that, we will have student presentations. Yeah, these students are gearing up to give lots of presentations on new topics which they have learned in only past 2 days. Huh? So we all look forward to that. Those who are not participating in the presentations, they should still participate in the as audience. Yeah. And then there will be a closing ceremony tomorrow. After the lunch break, we'll have a talk by Professor Nick Bezanishvili and a tutorial on his part of lectures. Maybe. Okay, thank you.
Amit, are you there? Hello? Amit, are you there?
Hello. Hello, Marcus. Is it Marcus? Yeah.